hypothesis test with larger samples, example 6. In order to test whether Maddie has extrasensory perception, or ESP, Maddie was asked to identify without looking the shape on a card as either a circle, a triangle, square, star, or wave. Thus, if Maddie is just guessing, Maddie has a 1 in 5 chance of just guessing correctly, because we have 5 different shapes, and if Maddie's guessing, has a 1 out of 5 chance of being guessing correct. So the null value, P0, 1 over 5, 1 divided by 5 is 0.2 or 0.2, and the other null value, 1 minus 0.2, 1 minus 0.2 is 0.8, and that would be the proportion that Maddie would get incorrect if in the long run, if Maddie is just guessing. In the sample proportion, in 60 tries, Maddie correctly identified 15 out of 60. So 15 divided by 50 is 0.25. So Maddie actually got a little bit higher proportion correct than when we would expect by just guessing, but that could have happened by chance. So we want to do a hypothesis test to see whether this provides evidence that Maddie has extrasensory perception. Okay, so the null hypothesis P would be equal to 0.2. In the long run, Maddie would get just 0.2 correct. That would be Maddie is just guessing, versus P is greater than 0.2. So this is a right-tailed test. We would only think that Maddie has ESP if Maddie gets more than 20% correct in the long run. Okay, so we want to check to see whether n times P0 and n times Q0 are both at least 5. So our sample size is 60. 60 times 0.2 is 12, and that is greater than or equal to 5. That's a yes. Okay, and then 60 times 0.8 is 48. That's also greater than or equal to 5, so that's also a yes. So because we got 2 yeses there, we can proceed to the next step and use the z-table. Otherwise, we would have to use exact binomial probabilities, such as, for example, a tree diagram. Okay, so since we're using the z-table, we need to compute the mean and standard deviation of p hat, and then we can compute the z-score. So if h0 is true, then the proportion that we expect Maddie to get correct in the long run is going to be 0.2. That's p0. And then the standard deviation of p hat, p0 square root of p0 times q0 over n, so it's 0.2 times 0.8 divided by 60. And so just on the calculator do the second square root, 0.2 times 0.8 divided by 60, and that comes out to be approximately 0.0516397778. Okay, so then we can compute this test statistic. It's a z-score. It's basically the same formula that we were working with earlier in the semester. It's the score minus the mean divided by the standard deviation. In this case, our score is going to be a sample proportion, which is 0.25, and the mean of p hat, if h0 is true, is 0.2, and divided by standard deviation of p hat, which is 0.0516397778. Okay, so do the subtraction first and then the division, and we get a z-score of approximately 0.97. And sometimes you'll see this formula expressed without the subscripts. So you might see, instead of P0 and a Q0, you might see a P and a Q. That's a little bit more ambiguous, but if you just understand from this context, but by P we really mean P0, and Q really means Q0, then you know, it's a little bit less handwriting, I guess, if you don't include the zero subscripts. In any case, it's the score minus the mean divided by the standard deviation. We get a z-score of 0.97. So then we want to look this up in the table. Because we have a right-tailed test, our alternative hypothesis that has a greater than symbol, but our table is left-tailed. Just the way our z-table is set up, it's a left-tailed table. And that's a common way of setting up a z-table. But that means we have to take the opposite sign of our test statistic, and we'll look in row negative 0.9, column 7 of the z-table. So we want the probability of z is greater than 0.97. They're giving a z-score that high if h naught is true. That's actually the right tail of the bell curve. 0 is in the middle. The positive z-scores are on the right. But because of the symmetry of the bell curve, that's actually going to be the same score as same value as a negative 0.97. Probability z less than negative 0.97. So we want to look in row negative 0.9, column 7 of the z-table, and it's in row negative 0.9, column 7. We get 0.1660. So that's our p-value of p-value is and that's more than our desired level of doubt. Alpha is 0.05. So that means we fail to reject H naught. There's not enough evidence to say that Maddie has ESP. So strictly speaking, we never accept H naught. Either we reject H naught or we don't know. In this case, we don't know. Maybe the sample does not provide enough evidence, but it could be that Maddie actually does have ESP. Okay, so I want to talk a little bit about the types of errors here. This tree diagram represents the possible outcomes from hypothesis testing. Either H naught is true or H1 is true, and either we don't reject H naught or we reject H naught. So there's 4 possible outcomes. H naught could be true and we don't reject H naught. H naught is true and we reject H naught. That's called a type 1 error. H1 could be true and we don't reject H naught. That's a type 2 error. H1 could be true and we reject H naught. 1 minus alpha is our desired level of confidence. Alpha is the Greek letter representing the desired level of significance. I like to call it the level of doubt. It's also the probability of a type 1 error. So the alpha here is the probability of a type 1 error. Beta is, our p-value is the actual level of doubt. Beta is Greek letter representing the probability of a type 2 error. And 1 minus beta is the power. Usually we do not try to compute beta or 1 minus beta. You have to make some additional assumptions in order to compute those values. Anyway, in this particular example, we did not reject H naught, so that means we take a chance of making a type 2 error. So in this particular example, is it possible we made a type 1 error? No, because we failed to reject H naught. If you reject H naught, then you take a chance of making a type 1 error. Is it possible we had a type 2 error in example 6? Yes, because we failed to reject H naught. And the best way to lower the chance of either type of error would be to increase the sample size. But the drawback to the larger samples is that they're more expensive. So anyway, you always take a chance of making some kind of error. If you reject H0, you take a chance of making type 1 error. If you don't reject H0, you take a chance of making type 2 error. So either way, there's always a chance of making some kind of error. And that concludes this presentation.